So again, I'm Michel Matari. I'm a student at the University of New York. Some of you may know me from OpenRest from last year. I have ported items to OpenRest and joined PGA, ORCONF, for seL4. This year, I have been participating with Google Summer of Code with Glorious project. Thanks to them and Google, I have been porting seL4 microkernel to REST-5 architecture. So that's what I'm going to speak about today. So I'll speak about seL4, why security matters, some details about seL4 microkernels in general, seL4 details, design abstractions, what has been done on the project so far, and some future ideas. So what is seL4? seL4 is the world's first operating system kernel to be formally verified. That means that it has no bugs by mathematics, proven by mathematics. So seL4 stands for Security Embedded L4 Microkernel. Security matters not only on desktop or Linux, but also in embedded systems and microkernels. It's fundamental to some embedded system applications like smartphones, like medical devices, security network systems, unmanned vehicles. It's known as the more the lines of code, the more the bugs. So microkernels have been developed initially with the multi-principle in mind to avoid the number of bugs and the number of lines of codes. Okay, so I'll speak about some history, brief history about L4 microkernel in general. It has been started by Ledka. He is a German scientist back in the late 18th and 19th. It has been developed with minimality and high performance inter-process communication in mind. This is a quotation from his paper back in 1995. It is saying that only the microkernel should have the parts that is needed and can't work outside the privileged mode. That's mainly what is microkernel about. Since 1993, microkernels, L4 microkernels has been deployed on safety critical system and large scale. So this is the main difference between monolithic and like Linux kernel and L4 microkernels. So in monolithic kernels and Linux, the kernel mode or the kernel part include device drivers, virtual machine, virtual system, inter-process communication, file systems, virtual memory scheduler, and applications communicate with the kernel using only system calls. While in microkernel, the kernel itself only includes basic inter-process communication, virtual memory management, scheduling, and applications are communicating with each other using inter-process communication, as well as with the kernel. The main difference between Linux and microkernels are that device drivers are implemented in user space and servers, so you can run a Linux server on top of the microkernel virtualization of them. So a brief history of microkernels. So it started with Ledka back in the early 1990s. He has developed his L3 microkernel. It was completely written in assembly for x86, and then he developed another version called the L4 microkernel. It was written completely in assembly. So right after that, it was proven that inter-process communication is efficient. It was 10 times faster before the microkernel version, before the L3 version. Well, I have to clarify what these colors are. So the two boxes are from University of New South Wales and Nesta. These are from Australia. IPM and Karlsruhe, and Dresden University and OK Labs, Open Kernel Labs. So right after Ledka's L4 microkernel version has been proven that it is efficient, University of New South Wales and Nesta have rewritten it to MIPS and Alpha. These were 64-bit. The L4 MIPS 1 was the first microkernel version to be written in C. Before that, it was an assembly. The Alpha one was the first one to support multiprocessing. When Letka moved to IBM, he has started developing his own microkernel version and called it X version. The X version, the main problem with X version was that IBM was forcing some intellectual property and patents restrictions. So that made Dresden University to develop their own version of microkernel, and they called it Fiasco. It was the first kernel to be written in C++. Yeah. And it is all the ones that is actively maintained so far until now. After Letka's move to Karl Shura, has developed and his students hazelnut microkernel, and it was written for Pentium, and this was the first one to be ported, not rewritten, to ARM. After Letka's death, his students started to develop their own microkernel version. So Pistachio was written in C++, and it was written to run on x86 and PowerPC, and University of New South Wales and Nesta have ported it for MIPS, Alpha, and ARM. Open Kernel Labs, before that, University of New South Wales have retargeted Pistachio to run on resource-constrained embedded systems and called it L4 embedded. It was the first commercial one that used by Qualcomm to run on wireless model processors as a firmware. Open kernels, or OKL4 microkernel was running mainly for virtualization purposes, like Nova. Nova is developed by Dresden University, and it is heavily dependent on Intel hardware virtualization. Back in the late 90s, capability-based has been known for its good security for access control. So they have been trying to adopt capability-based in Fiasco, but it wasn't originally written for capability-based in mind. So University of New South Wales started to develop its own from scratch kernel, and that's seL4, that I'm going to speak about today, with safety, minimality, and security, and capability-based in mind. One microkernel version that worth mentioning is PyOS, which is commercially used, and it is used on safety-critical systems, trains, aircrafts. Okay, these are some tables showing that inter-process communication on different targets with different microkernel version. Most notably, the Pistachio on Itanium target, or Itanium processor, is taking 36 cycles for inter-process communication, one-way inter-process communication, while in Hazelnut, Pentium 4 is taking 2,000 cycles. So that's target dependent. When it comes to minimality principle, seL4 is achieving pretty much good. It is about 10,000 lines of codes compared to Fiasco, which is 40,000 lines of codes. Okay, overview about seL4. seL4 is formally verified, no bugs. It's open source, it's capability based, it's simple, and 10,000 lines of codes compared to other versions of microkernels or full microkernels. It is using inter-process communication and new feature called endpoints, which previously it was only synchronous way of inter-process communication, but endpoints is using synchronous and asynchronous way to communicate. seL4 has been written to run on ARM and x86, and I have ported it for RISC-V. The microkernel itself, seL4, wouldn't be of much use without applications and libraries that run on top of it. So there are a few projects that run on top of seL4. The verification project It's the one which proves that seL4 microkernel is bug-free. Most interestingly, it's 100,000 line of codes, while the microkernel itself is just 10,000 line of codes. seL4 test is another project that tests seL4 kernel's feature. Some componentized architecture for embedded systems, virtual machine manager which was written for x86 or A32, and again it relies on Intel virtualization technology. A reference OS, it's an example of operating systems that run on top of seL4, and finally assembled operating systems, which is used by University of New South Wales, part of advanced operating system course. And it is advised that anybody who wants to learn about seL4 programming to follow this course. And this, by the way, was working on seL4 on RISC-V. seL4 has some components, abstract components and modular components. It's mainly thread management, address space for virtual management, inter-process communication, device primitive for implemented device drivers in user space, capability, of course, capability space management. So because it's very modular and these are abstract, any efficient piece of software can replace one of them, or even hardware, right, like capability-based hardware from Cambridge. So this is the typical structure of seL4 project. So the microkernel is working on privilege mode. There are some libraries provided by seL4, which as a project may or may not use it. The servers can run on top of the libraries, can make use of it or not, and the applications can communicate with the libraries and seL4 microkernel and the server using inter-process communication. For example, a simple operating system can run as a server in here, and the microkernel is running on the privilege mode. The libraries are the server can make use of the libraries, and applications can make use can communicate with SOS, a simple operating system, as a server and applications. From runtime perspective, this is an example of a RISC-V seL4 board which is running. So the first one which takes control is the 8 bootloader. It's running on machine mode on RISC-V and is loading the seL4 microkernel from the archive. After this, it's the kernel bootstraps initialize memory and type memory, and seL4 start the root task. Diagnosis is taking control, and then SOS as an operating system is running as a server, and this is an application running as an application and communicating with some operating system using inter-process communication. Questions? This is a roadmap for seL4 in general. Most notably 64-bit support will be released this year, ARM virtualization, and safety critical systems. Yeah.
Actually, what are the x86 use cases? How come they're so keen on x86?
x86 use cases, there is a virtual machine monitor that is currently running on x86, but not 64-bit yet. 64-bit is currently under development, and they said they will release it soon. And ARM virtualization. Multi-core support. There is a multi-kernel mode currently on x86, only x86, but it's to be removed from the microkernel, and it will be on user space.
Another good question, how come there's no other architectures supported? Do they exist but they haven't been upstream?
No, only seL4 has been initially written for x86 and ARM. There are no other ports. So I have, and my RISC-V, of course, so there are no other ports other than this, because it's new. It has been released on 2009.
It's 6 years ago.
It's pretty recent.
Yeah. Source past year.
Yeah.
Oh, really?
It has been open source last year. Yeah. They are hiring, by the way. That's it. Okay, seL4 on RISC-V. This is the current status. seL4 runs on RV32 mode. It runs on Spike, Joke, and it is running on Rocket Ship. But the main problem with Rocket Ship was at 64-bit only, so I had to do some tricks with the layout of page tables, 64-bit entries. And then I have run SOS, some operating system, as a use case in user space that's running on seL4 board for RISC-V. And applications, of course. This is a snapshot of SOS running on Spike. I have written how to build and run the port, detailed step-by-step instructions how to build it and run it. I know, okay, this is RISC-V modes, this is machine mode, this is hypervisor mode, and this is supervisor mode, this is application mode. There were some discussion at first where to put seL4 microkernel in which mode. First, yes, suggested to put it in machine mode, but the problem was that other versions were ARM and x86 were running and assuming MMU based and page table based memory management. So I went for supervisor mode right away. This is the one that seL4 is currently running on, and applications are running and servers are running in user mode. There are other options which I didn't illustrate. The hypervisor mode maybe, but it's not implemented yet, I think. Yeah. So the first one is the currently one that is running and working. Okay, these are the libraries that are involved with RISC-V and the board mainly. libseL4, which acts like glibc for exporting the seL4 system calls. libmusclec, I had to port it to RISC-V port, but it's not upstream yet. libmusclec, okay. There's archive, CBIO archive to archive the kernel and the binaries and the servers. And SOS, same operating system. This is a mapping, actual mapping, memory mapping for the microkernel. So here is the microkernel and the untied memory, which means that free memory is taking 256 megabytes. It is mapped in here. This is a physical memory and this is a virtual memory. The EL4, which running in machine mode, is taking place in here, the lowest physical memory part. Okay, because you like demos, I have I'm running on seL4, and these are some applications. So here the ELF loader is running the first, and then it loads the microkernel from the CDIO archive. The kernel puts
Can you make it bigger?
bigger? I don't think so. It's a terminal. Okay.
Was that extra? Oh.
Okay.
I don't think so. Okay. Okay, so
Control Shift plus equal. Control Shift plus equal.
yeah, I have tried it, but it's not working. It's usually work. So yeah, the ELF loader is working the first, and then it loads the microkernel, seL4 microkernels. The microkernel puts traps and initialize memory and stuff, and then the root task takes control, which is in this case a simple operating system. It prints out some data about the untied memory and capabilities. And after this, it loads the applications, which is TTY, just print out hello world, and that's it. Okay, these are some discussion points and future ideas that can build on the seL4 microkernel. Cambridge are developing some hardware capability which can be replaced by software converted in seL4, and it will be good for performance, minimality, and security, of course. We can offload some seL4 apps from the master course when the minion course are available to the minion course, and the apps, seL4 applications are running on the minion course, and system course can be redirected to the master core. Formal verification. Only the ARM board is formally verified. Even x86 is not formally verified, so it will take a lot of time, and I'm not an expert with Haskell and Isabelle to formally verify the RISC-V, so maybe in the future I can consider it, or anybody else. There are a lot of virtualization opportunities, mainly because microkernels have been known to work with power virtualization and running Linux, seL4 Linux on top of it. And there is a project VMM that is running already in x86, so maybe it can run with RISC-V, maybe on hypervisor mode or whatever. Trusted execution module, which Stephen, you can know about it from low-risk documentation. We can support multi-kernel and multi-core support on RISC-V port. That's pretty much it. Thank you. Questions?
Questions?
About the formal verification, you said that it is not part currently of what you have done. Do you have any idea how much work it would be? Because the other figures you show that it's 10 times the work, or at least 10 times the amount of code that is required. So how much can you reuse from that?
From the, well, pretty much, because the kernel version, the target independent parts, I assume it's not very big, so yeah, I can use on target independent parts of formal verifications. For the RISC-V, I'm not sure how much effort will it take, so I didn't go through it anyway.
Do you have to fully verify it to get it upstream?
No, I have actually been trying to upstream it, but because there is a new privilege mode that is to be released, 1.8, so I hold it off until it is released, and yeah.
Right. So you mentioned that on x86 the virtual machine monitor is a quite popular application. How would you see? How would you see this working on RISC-V?
I don't know.
I guess it will make use of the hypervisor mode, or.
But the hypervisor mode is not implemented, so we can run it. We can still run it on the supervisor mode, I think, but or even the machine mode, because the machine mode, as Jim mentioned, it doesn't need the hypervisor doesn't need translation, only noise detection. So yeah, I think it can run on machine mode or supervisor mode for now.
About the formal verification, I was curious about which properties are actually verified, or if you have any information about where, or if it's, I can see it somewhere.
How it is formally verified?
Yeah.
Yeah, sure. The code is part of this project. The first project, it is already there on GitHub on seL4 repo. So you can see it and see the Isabelle and Haskell and whatever they are coding in. And yeah.
Is there any documentation about all this? Do you know about?
There are a couple of papers about verifications, but documentation, detailed documentation, I'm not sure.
Thank you.
Any more questions? Good, we should probably leave that. Next session. Awesome.